Okay, so last time I had barely finished the lecture on digital building blocks. I'll just go over that real quick. I've got a quiz posted on that for this week. So we talked about adders, ripple carry adders. I think everyone's familiar with that from 211. We talked about the carry look-ahead adder, which is where you propagate and generate bits from each column, and then you can assemble those together from multiple columns to generate ranges of propagate and generates. But the ranges are just like segments, in this case 4-bit segments, blocks. Now, one thing I said last time, I might have confused you a little bit. Within these, basically the idea is that you take your adder and you divide it into, in this case, 4-bit blocks of 4 bits, blocks of 4 columns. And then you generate the propagate and generates from each block, right? So you have the time here for the carry look ahead. The critical path delay is the propagate and generate for the individual bits. And then you take those and you generate the block propagate and generates, right? So for that block. And then once you have those, you use those to determine the carryout for that block as a function of the block level generate and propagates, as well as the carry in into that block. Does it make sense? Okay, so the problem is that you still have to go through. So when you have the carry in from the previous block, you can arrange this logic so you only have to go through 2 gate delays in each block in order to generate the carry out. Does it make sense? Right? So this part is the part that is going to be multiplied. That delay is going to be multiplied by the number of blocks you have. This n over k minus 1. N is the total bits, k is the block size. So in this case, if you have a 32-bit adder and 4-bit blocks, you'll have 8 of these blocks. And so you'll have to propagate through 7 n minus k minus 1. You have to go through 7 of these guys, right, to complete the whole circuit. That's not too bad, right? But then we talked about this prefix adder. And the prefix adder's goal is to also build up these generate and propagates for blocks. But instead of just doing it in 4-bit blocks or 4 k-bit blocks, they're built up incrementally, first from pairs of columns, and then so that first level you get pairs of columns, so you get propagate and generate, for example, like bits 14 down to 13, right? And the goal is to get the propagate and generate for every single final bit, every column. So your goal is to get the generate for this column 2, you want to get for bit 2 down to -1. And the generate for -1 is the carry in, is the top level carry in. So the idea is that if you can calculate the generate for each one of the output columns separately, then every single full adder is going to have its own carry in that's going to be constructed from building up combinations of the propagate and generate bits that are in groups. You guys with me? And this is all done through combining together 2 groups. Like in this case, we have 14 down to 13 and 12 down to 11, and you can combine those to get 14 down to 11. And then 14 down to 11 can be combined with, it can be combined with 10 down to 7 to get 14 down to 7. Right? So you can make these you can join these groups together arbitrarily in order to ultimately your goal is to get each bit down to -1. right? And these are the carry in. So if this is a 16-bit adder, the 15th full adder will have a carry in that will be the generate that's 14 down to -1. You guys with me? Now, once you get down to this bottom level, you don't care about propagate, but you do need propagate for all these other black blocks. Make sense? So the delay here is the log base 2 of the number of bits. So you have to go through, for 16 bits, notice you have to go through log base 2 16, which is 4. So you have to go through 4 stages of those propagate, generate calculations. Right, which it turns out it's really just this, right? So what you're multiplying by, you're multiplying the delay of just this by, in this case, 4. So this is a very fast adder. Make sense? It looks a little confusing when you look at the fact that these propagate, like if you look at this, you look at propagate and generate 14 down to 7. It's 14 down to 7, and you think, oh, that's a multi-bit signal. But keep in mind that each one of these black boxes only generates 2 bits. So you're generating a single bit that represents the propagate for a range of bits and a generate for a range of bits. Okay, so don't let that range there is not meant to mean that there's a range of, like these are buses, like these are multi-bit signals. They're not. These are all single-bit signals, but they're meant to represent, they're calculating the generate and propagate for a range of columns, right? Okay, so that's the prefix adder. Then we looked at some examples of how to calculate delay for those, and we talked about subtractor, which is just an adder where you take the 2's complement of the second input. We talked about comparators, which is in the book. This figure is from the book. They're doing a, what is this? XNOR gate. They're doing an XNOR between each pair of bits, and then they're fanning. What XNOR is true if the inputs are the same, right? That's an XNOR, and then they're feeding all those into a big AND gate, right? I mean, see, when I looked at that, I was like, that can't be a good way to build a comparator, right? Because if you look at the one we use in class, we do a subtract. You know, we subtract A minus B, and if the result is 0, then the numbers are equal, right? But then I thought about it, and I'm like, well, maybe that's not a best way to do it, because think about it. If you subtracting A and B is a lot more expensive than just taking the XNOR of each individual A and B bit, right? And then you might say, yeah, true, but what about this giant fan in here? You got to have this gigantic AND gate that takes in 32 inputs, right? That's no good. Yeah, but you need the same thing for the subtraction method too, right? Because in the subtraction method, you have to check to see if all the, like if you have A minus B and they're 32 bits values, then you have to send all those 32 bits into a single, like an OR gate, right? Or a NOR gate, right? Because you want to check, make sure they're all zeros, right? So I don't know if the way we do it in class is any better. Actually, it might be worse. This might be better than the one that we've gotten in our ALU, right? I haven't really done, an in-depth analysis, but when I think about it, this might be a better way to do it. Either way, comparisons are pretty expensive because ultimately they involve a reduction where you take a bunch of bits and reduce them all to 1, right? Which involves a fan-in. Fan-ins are expensive. In reality, you will never have a 32 input AND gate. It's impossible. So the way that this is done in practice, if you put this on an FPGA, this AND gate will get split into multiple AND gates that will be staged in multiple stages. And then those stages, will probably be like a binary tree. So you may have like 5 stages of ANDing in practice, right? Maybe not an FPGA because you got 6-bit LUTs on an FPGA. But either way, this is the hard part, the expensive part of a comparator. Okay, less than. If you want to know if A is less than B, you kind of have to subtract. I don't know how else you could. I mean, at least for signed or even unsigned, yeah, you have to subtract, right? Check the signed bit of the result. And then we talked about shifters. This is a barrel shifter, but it only shifts one direction, right? This one shifts. This one shifts which way? A0 goes to Y0 if the shift amount is 0. But if the shift amount is 1, then A0 goes nowhere, right? Because remember, if you have wires crossing and there's no dot on the wires that cross, then they're not connected. But if you have a T, like you have here, then there's a connection, right? That's the schematic rules that the book uses, at least. So if you look at A0, A0 is only connected to this one mux, right? So if the shift amount is anything but 0, then A0 is gone. It just gets, it doesn't get pushed to the Y's. It doesn't get pushed to the output. It essentially gets blocked in this circuit. And the reason for that is because it's being shifted out. So this must be a right shifter, right? So like, for example, if you look at A1, if the shift amount is 1, it's going to go through this input on this mux, right? So A1, here. A1, right, there's your connection between A1 and this mux. So if the shift amount, remember the shift amount is the select on these muxes. So if the shift amount is 1, I'm going to take A1 and I'm going to send it to Y0, right? So A0 is going to be sent to a less significant bit, right? It's going to be shifted to the right. Make sense? So that's a barrel shifter. Again, it's a pretty expensive piece of hardware there. Some processors don't have barrel shifters, like lightweight embedded processors. Some of them don't even have a barrel shifter. In the NEOS processor, if you guys, I don't know, some of you took 313. In 313, we use a embedded processor that's kind of an off-the-shelf IP for the FPGA, and you can choose whether you want to include a barrel shifter, because if you don't need it, it's more efficient to not include it in the hardware, right? And there's other architectures, by the way. There's transistor level designs for barrel shifters too. This is kind of one that's built from muxes. Okay, and then we talked about shift registers. Now these are kind of cheap. Shift registers are just a bunch of flip-flops connected in series. These ones are kind of cheap, right? They're just point-to-point connections. But the problem here is that you can only shift one bit at a time, right? It's not a barrel shifters can shift an arbitrary number of bits. A shift register can just shift one register. But shift registers are used a lot to create delay lines, and also, in this case, you can create a parallel to serial converter. You can load in data in parallel and then shift it out in serial, right? So this is what happens with your HDMI connection, SATA connection, like when you plug your monitor in. The CPU sends pixels to the monitor in parallel, and they're shifted out in the HDMI cable. It's one bit at a time, right? Same thing with SATA. That's for hard drives, disks. That's a serial protocol. So anytime you have to do a parallel to serial conversion, use something like a circuit like this. Okay, and then we talked about multipliers and dividers. Okay, now the multiplier design we talked about is, the idea with this is you're basically just using these AND gates to turn off, to basically zero out one of these things that you're adding, right? One of these rows you're adding, depending on the multiplier. So if any of the bits of the multiplier are 0, for each one of those bits, you need to zero out the corresponding row down here, right? And that's basically what's happening here. So you have A, and A is going into, is coming in, and then you are adding A to itself with these first levels of adders here, except it's you've got these AND gates which are controlling whether you're turning on A or not turning on A into that adder level, right? Does it make sense? So basically, each one of these rows is equivalent to one of these rows. So that's why these are shown together. This is literally just that, right? It's even at the bit level because all the A's and B's are all bits, right? So basically, if you look down a column and you add your partial products here, you have each one of these each one of these columns is implemented through adding through these full adders. Does that make sense? Now, you might notice here, wait a second, there is one difference though. You notice there's just 3 layers of adders here, whereas we have 4 rows here. And the reason for that is because the first row actually, if you look at this first row of full adders, this actually is taking care of these first two rows here, right? But then for every additional row here, you need to have, 1 row full adders, because you have to add the partial sum from the previous row. Okay. So multipliers are also expensive. If you have a 32-bit multiplier, you basically need 31 adders, right? I mean, assuming you use that architecture. And then for division is probably the most expensive operation, because you have this basic issue where you have to take the divisor and shift it to the left relative to the dividend, right? Now in this case, we're actually doing the opposite here. We're taking the dividend, which is A. A is the dividend. That's the bigger number that you're dividing into. And we're shifting it right. That's why you see A3 there, right? See that A3 is in the top layer? Why A3? What happened to A2 down to 0? Well, those are not being considered in the first layer. We're just taking A3, right, which is the version of the multiplicand shifted to the right. Now, you might say, why would you do that? Well, it's the same thing you do. It's the same thing you do here with grade school division. See, basically the idea is that if my dividend is this bigger number here, what is that? 10 plus 3, 4, 5, 6, 64, 74, I guess? Yeah, I think that's like 74. And we're dividing 8 into 74, right? The 74 is the dividend. And the idea is that we want to subtract the divisor from just the most significant bit, right? You see, most significant bit, right? Now, if you were doing this by hand, you would just skip this step, because you know that you're not going to be able to do that subtraction. But the hardware doesn't know that. So it's going to take the divisor and subtract it from the most significant bit of the dividend, right? And then if the result is negative, it has to undo that subtraction. It has to restore the result it had prior to the subtraction. You guys with me? Okay, so that's why they call it a restoring divider. So basically, I'm trying to subtract 1 minus 8. I can't do that, so I'm going to restore it. Then I say 2 minus 8. Nope. 4 minus 8. Nope. 9 minus 8. Now, every time I subtract, I'm shifting the dividend to the left by 1, right? Finally, I get to the point where I could subtract and get a positive difference. And when that happens, what am I doing? 9 minus 8 is 1, right? So once that happened, then I keep the difference. It's 1, right? Should be 1. Yeah, it should be 1. I think I might have screwed that up. Yeah, I should have kept that one as 1. Sorry. Yeah, so basically after when you subtract and you're successful, you want to keep that difference in place of the original dividend. It becomes your remainder register, right? That's the idea. So, yeah, I don't know why I didn't know why I kept that 1 in there. I should have. But in this design, the idea is that as you propagate down, the results that you get from each row of these blocks is going to be the remainder, which is the difference that you got from subtracting the divisor from the shifted form of the dividend. And you'll notice that we're shifting the dividend left. That's why you have A2 coming in, A1, and A0. And then as you go down, these lines go diagonal that implement the left shift. Does it make sense? So the problem here is that divider is going to require subtractors, right? 32-bit divider requires 32 subtractors, but not only that, but it also has to have the restoring logic too, the comparison, the comparator, and the restoring logic. So divider is expensive. When I first started developing this class, we put a divider in your ALU, and we couldn't make that happen because it used like nearly all the logic on the FPGA, right? The reason is because we're trying to do it combinationally in one cycle. If we had done a multi-cycle divider, that may not have been the case, but we didn't want you to have to worry about operations that take more than one cycle. We wanted your ALU to be one cycle. You guys, does it make sense? Okay. One of these days, we may figure out a way to do divide in this class. Okay. All right, and then I'll cover that. Okay, any questions? So that's the digital building blocks. Okay, so now we're going to move on to another topic, which is transistor level logic or CMOS logic. I want to talk about that a little bit. So I used to teach a class on this called VLSI design, which was like designed for ASIC, like chip design, as opposed to like, in this class, obviously we target FPGAs, but if you wanted to fabricate a custom chip, you'd have to design it for manufacturing, right? You would have to design it. So there's this process you go through, which is where you can still synthesize HDL code, but instead of going to mapping to LUTs on the FPGA, you map it into a cell library, which is the little digital logic cells, little footprints that you put on the ASIC. But the question is, how do you build those cells? How do you build a gate on an ASIC, on a CMOS chip? How does that work? Okay, well, first of all, before we get to that, I want to talk about logic levels for a minute. So the digital logic levels have changed over the years. It used to be, back in the 70s and 80s, a Boolean 1 or logic high level was 5 volts. And that was, what was that called? TTL logic, I guess. Yeah. So VDD is the supply voltage. That's logic, basically logic level 1. And just ignore these columns. I'll talk about what those mean in a minute. But we went from 5 volts with TTL logic. TTL logic was actually a different way to build gates from transistors. But even the first generation of CMOS logic used 5 volts, and then eventually it's been kind of going down. I think nowadays it's like less than a volt. Like it could go as low as 0.9 volts, although modern CPUs actually dynamically adjust that. So whenever you need to speed up your CPU, you increase the clock rate, but you also increase the supply voltage, right? So you do voltage and frequency scaling, right? But the lowest voltage you'll see, could be 800 millivolts, something like that. And the highest you might see is maybe 1.2 these days. So part of that has been the advances in the fabrication technology and the device technology. But another thing you have to consider with that is noise. So we have wires are subject to noise. And especially in a digital circuit, because whenever you switch a logic gate from 0 to 1 or 1 to 0, it temporarily shorts power and ground. So you get in fact, CMOS logic gates, and CMOS is the technology that's used to build gates on a chip, on a digital logic chip. It's designed to use very low power if you're not switching, right? If it's just putting out a 0 or 1. But if you switch from 0 to 1 or 1 to 0, there is a spike in current in that gate. And the problem with that is, one, it uses power. So that's where the main source, that's called the dynamic power consumption. But also, it will cause the power supply rail to dip a little bit, right? And if you've got a whole bunch of gates around each other that are switching, you get switching transients on the power supply. The power supply becomes noisy. Now you can mitigate that to a degree by putting capacitors, called decoupling capacitors, in there to try to take that noise out. But you can't really get rid of it entirely. And it's so bad that if you have a chip, a mixed signal chip that combines digital circuits and analog circuits, you have to isolate the analog circuits because the analog circuits will be affected by that noise. You have to have them on different power supplies, and usually you try to build a little moat around the analog circuits, a little diffusion area around them to try to block out some of the noise from the rest of the circuit, right? So digital logic circuits are noisy. So the problem is that in a perfect world, you would have your logic would work as follows. If any voltage value is from 0 to half the supply voltage, so let's say you have a 1 volt system, then any value from 0 to a half a volt should be a logic 0, right? And any value from a half a volt to 1 should be a logic 1, right? Ideally, that's how you want it to work, right? So this is a buffer. So a buffer is just the output is equal to the input, right? It's kind of like an inverter, except it doesn't invert. And so this is showing as I increase the A is the input, right? A is the horizontal line here, horizontal axis. As I increase A, the output Y is 0. So my A, let's say this is 1 volt, VDD is 1 volt. So as I go 100 millivolts, 200 millivolts, 300 millivolts, Y is just staying at 0, right? And then eventually I hit 500 millivolts, at which point I switches suddenly to 1 volt, right? That's how we want these circuits to work, right? So basically what that means is that means that the voltage input low, VIL, V sub IL, which defines the kind of the threshold for what is a logic low, logic 0, right? That should be VDD minus 2, right? And VIH, which is the minimum voltage for a logic high, should be the same value, right? Does it make sense? So there's VIL, voltage input low, and VIH, voltage input high. Voltage input low is the voltage under which you have logic 0, and voltage input high is the voltage over which you have logic 1, right? Okay? And then the output of that gate should just always be 0. The output, which is VOL, voltage output low, should be 0, and voltage output high should be 1 volt, right? Ideally, right? But in reality, this is really the kind of curve you see in a real gate. So what happens is that as you start increasing the input voltage, the output voltage starts to rise gradually, right? And then at some point, you get this really sharp increase, right? And then it slowly starts to converge again towards VDD on the output, right? So you get this kind of S shape, sort of, right? And so what you end up with in reality is if you look at the point here where you have what's called unity gain, which is where the slope of the trace of this line is 1, right? That's like the elbow of the curve, essentially, right? Where the slope is 1. That's where it changes. It's where you have, it sort of starts racing up, right? If you look at the voltage where that happens, that's really your VIL, right? So as long as your input voltage is below the unity gain point on, in this case, a buffer gate is used as the kind of the model for this, right? As long as you stay below the unity gain point, which is VIL, fine, right? And then for voltage high, you want to be above the unity gain, the other unity gain point, the other point where the slope is 1. That's VIL. So you want to be below VIL. and you want to be above VIH, right? For the input, always. And anything in between those two is called the forbidden zone. You don't ever want to be in the forbidden zone for an input, right? Okay, now likewise, the output of the buffer, its voltage at that unity gain point is VOL, right? Now VOL, luckily, is lower than VIL, right? What that means is that the logic gate's going to keep the voltage pretty low for a while as you increase the input voltage. So VIL could be like, it could be on a 1 volt system, it could be, say, 400 millivolts, right? But VOL could still be like 50 millivolts, right? So even if I start pushing that input, pushing it and pushing it and pushing it, the output still stays kind of low, right? Right? And then suddenly it'll fly up to, at VIH, when I set the input voltage to VIH, which might be, say, 600 millivolts, then the VOH will be pretty high, right? It's not going to be all the way at the top, but it's going to be pretty high, and that's your VOH, right? So what this means, the implication of this is this gives you a noise margin. It allows the gate, basically to sort of clean signals up that have noise on it. So you've got noise on the input, and that noise on the input looks a little better when it comes out on the output, right? So this shows like basically the VOL is shown here. Like if you show this from the bottom is 0 volts and the top is VDD, the supply voltage. VOL is like a small sliver at the bottom, right? So that means the gate output will be in this range, right? And the gate out for logic low, and for logic high, it'll be in that range, right? As long as the input is in this range or that range, right? This range is between 0 and VIL, and this is VIH and VDD, right? So as long as the input is in this range, out of the forbidden zone, then your output will be in this range, which is even wider. The difference between those two is called the noise margin. So the difference between VIL and VOL is the noise margin low. And the difference between VOH and VIH is the noise margin high, right? That's basically how much extra noise you can add without causing problems, right? Okay? Yeah, so the idea is that so you can add noise here to this input, right? Which will add some noise to that output, but it will reduce the noise, right? So then I can still add extra noise here to this middle wire before it gets to the receiver. That's the idea of the noise margin. Does that make sense? So basically, it's essentially the amount of noise you can tolerate on your wires. Okay, any questions about that? Okay, so let's talk a little bit about silicon. So silicon is an element, and it's a semiconductor, which means that it conducts, it semi-conducts electricity, kind of, a little bit, not much, right? In fact, semiconductors are really not good conductors at all, actually. They're pretty horrible. So silicon is, what ends up happening with silicon is very abundant on Earth, but it usually is in the form of silicon dioxide, which is sand or glass, right? You don't usually see silicon by itself. In order to get pure silicon, you have to grow it. There's a manufacturing process that creates, you basically grow silicon in an ingot, which is like a cylinder, which then you cut wafers out of to make chips. But you're not going to, I don't think you'll ever see pure silicon in nature, but you can grow it. pure silicon. Silicon is it's in the group, or it's in the column 4 of the periodic table, which means it has 4 valence electrons in the outer shell. And when you have a pure silicon, it forms a lattice, it forms a crystal, where each atom forms covalent bonds with 4 neighboring atoms, right? But the crazy thing is, because it's a crystal, each one of the bonds is at a specific angle. The bonds are at an angle. So what you end up with is this thing that looks like this, which is this kind of crazy structure in here. And the structure repeats. It's a repeating structure. And the smallest unit of repetition of that structure is called the unit cell. So this is the unit cell. I think there's, I forget how many atoms are in it. 1, 2, 4, 6, 8, 10, 12, 18 or so atoms, something like that, in the silicon unit cell. Okay, so you get this kind of cool structure. Now, the atoms are spaced apart in this structure 0.543 nanometers. And the whole unit cell is about 5 nanometers. Now, does anyone think does that raise any red flags for anybody? So you might have heard that like modern chips are fabricated on a technology node, they call it, right? They have different fabrication processes that have a fabrication node associated. And that fabrication node is essentially what they claim anyway, is the smallest transistor size, right? So you've heard of like the 90 nanometer process, the 45 nanometer process, the 13, then they had 18, where'd they go, 13. Anyway, right now, TSMC, who makes chips, embedded chips, and Intel, they're claiming they're down at 4 nanometers, right? Well, that's impossible, because the unit cell of silicon is only 5 nanometers. That's smaller than the unit cell, right? And not only that, but they're saying, well, we're going to go to 3 nanometers and 1 nanometer. The atoms are only a half a nanometer pitch, between the spacing between the atoms. So clearly there's something going on there. Those chips are not 7 nanometers. They're playing some games there with the numbers. I think they changed the definition of what that number, that number used to be the size of the transistor gate, the gate terminal in the transistor. That is no longer the case, right? So don't let them fool you. But it also means that, you can't shrink down your transistors. You can't go beyond 5 nanometers. That's the size of the cell. That's the size of the pattern in the silicon lattice, right? Okay, so I mentioned that silicon is a semiconductor, though. So pure silicon is basically hardly conducts electricity at all. But what you can do with it is you can dope it. So if you take an atom from column 3, which is going to be boron, aluminum, or gallium, you can blow it inside the lattice, basically. You basically you dope it. You take this high temperature, you turn this element into a gas, and then you put it into the lattice somehow, right? So when you grow the silicon, it starts out as pure silicon, right? You can't grow doped silicon, I don't think, unless someone came up with a new technology I'm not aware of. Silicon is grown as pure silicon. I mean, there's some impurities in it, but the idea is to make it a pure semiconductor. And then you change the conduction characteristics by doping it. And this is like nasty work. That's why they don't make chips in the United States. This is high temperature, poisonous stuff, right? So you can put these in, and what ends up happening is that ends up replacing atoms from this group 3, replace some of the atoms in the silicon lattice. And that frees up, well, actually, these only have 3 valence electrons. So what ends up happening is that it makes the lack of an electron in the lattice. So one thing I forgot to mention, when you form covalent bonds with these guys, the electrons in the valence shell, they're free to move. They're mobile. They can move. They can be, they're shared between these atoms. When you put in one of these group 3 elements in there, it creates a lack of an electron that can move around inside this lattice. And that ends up being a charge carrier. They call it a hole, right? It's like basically a missing electron slot can move around within that lattice. And so that makes the thing conductive, because that free hole can move charge, can transport charge, right? At a certain speed. It's limited. It can only move so fast. You might say, well, it moves at the speed of light, right? It's like a hole. It's an electron. No, it doesn't. It's much slower than that. It's not that fast. The speed at which a charge carrier can move is called the mobility, right? Likewise, if you put a group 5 element in there, there's an extra electron that can move around, right? So you end up with 5 valence electrons in one of these slots, and that can move around, right? And that's also can be a charge carrier, right? The more you dope it, the more conductive it is. You can choose how many of those atoms you want to replace with dopants, right? It's up to you. If you put in group 3 element, that's called p-dope. P-dope silicon. P standing for positive. Why positive? Because there's a hole. Hole is lack of electron, and electrons are negative. So if you put a boron in there, it becomes a p-doped. And if you put something from group 5 like arsenic, everyone's favorite element, arsenic, then it'll become a n-doped silicon, negative charge carriers, right? But either way, it just becomes conductive, right? Okay, so you have these two types of silicon. You have, oh, I don't have the, dang it, I don't have the, I thought I had a picture of a diode. I don't. Okay, sorry. So, all right, so if you take p-doped silicon and you butt couple it to n-doped silicon, that creates a diode. And what happens is if you put a positive voltage on the P relative to the N, right, the charge carriers inside this N, which are N, remember N is N, negative, electrons. Those charge carriers, those are the majority carriers, they start to accumulate to the junction, right? And likewise, the charge carriers on the P side, which are holes, which are represented as little plus signs, they go towards the junction. And so this thing then starts to conduct current, right? But on the other hand, if you reverse bias it, meaning you just switch the voltage, so put a positive here, negative here, the charge carriers move away from the junction, and it creates this, it creates an area where there's no charge carriers. And so it blocks the current. The current won't flow backwards, right? So that's a diode. Now, the thing that's a little weird about this is the next kind of step you have to take to understand this. The majority carriers in P are holes, right, as I mentioned. And the majority carriers in N are electrons, right? Those are the majority carriers, right? But there's also minority carriers. So even though P has all these holes in it, you also have some electrons in that too. You have some electrons in there as well, but not many. And you got some holes in the N-type silicon too. Those are called the minority carriers, right? How did they get in there? Unclear. They're contaminants, right? They're just in there, right? But the minority carriers don't play any part in the operation of a diode. So when it comes to diodes, it's just the majority carriers that make a difference here in the operation of a diode, right? However, the minority carriers do come into play for a transistor. So the way that you build a transistor is basically from diodes. You start out with, now, okay, one more thing I want to mention. A diode is just, you just butt couple two pieces of silicon together that are doped different ways, right? That's how you make a diode, very simple. Transistors, on the other hand, are built in a substrate. You start out with a substrate, which is your chip, basically, and you build the diode structures in the chip, right? And so whenever you see a picture of a transistor like this one, this is a cross-sectional view, like if you took a sandwich and you cut the sandwich in half and you looked at the side of the sandwich where you cut it. This is a sandwich view, right, where you cut it along its vertical axis, right? And you look at what makes up the layers, right? So these are the layers. So you end up with a substrate. Now, the substrate is basically the chip, the whole chip, the body of the chip. So as I mentioned, you start out with a silicon ingot that you grow, and then you slice it into wafers, which are discs, right? Then those discs are sliced up to become individual chips. But before you do that, you dope the entire wafer. And so the wafer is generally P-type silicon. You put the, what is it now? Aluminum? You put the boron, you put the aluminum, or you put the gallium in it, right? You make the whole wafer P-type. Why do they do that? I don't know why they chose P-type, but that's generally what you have in most fabrication processes. But you can reverse the doping in parts of the substrate. So these are called diffusion areas. These are little islands embedded in the substrate. They're little islands that you punch into the substrate. They don't go all the way through. They don't penetrate all the way to the bottom. They penetrate partly into the substrate, and you blast it with N-type dopants. And that reverses the doping from P to N, but only for these little diffusion areas. Does that make sense? Now, these diffusion areas are basically, these form a diode, right? Because they're coupled, right? They're touching each other. The substrate's P and the diffusion area here is N. So this creates a diode. Now remember, diode flows current from P to N, right? So what you have to do here to make these not connected is you have to make sure you ground the substrate. The substrate has to be at the lowest voltage possible because you want to make sure that this substrate voltage never rises above the voltage on the diffusion area, or boom, you get latch up. The chip basically blows up, right? So, but as long as the substrate is grounded, you have a reverse bias here, right? So you don't have that happen, right? Now, that's still not without consequence. There is a consequence to that, though. You may not be able to send current from the substrate to the diffusion area, but you still get a capacitor there, which has implications, big implications, right? Capacitor, remember capacitors when you have like two things next to each other where there's no direct connection between them, the dielectric in the middle. So you do get a capacitor here, but they're not conducting, directly connected, right? Okay, so then in between two diffusion areas, you stick a gate. And the gate is separated from the diffusion area with glass, silicon dioxide glass. That's an insulator. That's a straight up, that's the best, I think that's the best known insulator. That's the best insulator imaginable is silicon dioxide. I don't think there's any better insulator out there than that. So and the nice thing about silicon dioxide is that you can make these silicon dioxides by basically, you take the top of the chip surface and you heat it up, and it makes silicon dioxide. You oxidize the top layer. You might say, well, why isn't the whole thing covered with that then? Well, you create a mask. You do this process called masking, right? So you can mask off this part, and then you heat the exposed part of the substrate, and you can naturally create that nice insulating layer just by cooking it, right? Okay, and then on top of that, you put polysilicon. What's polysilicon? I don't know. It's what they make solar panels out of. It's a type of silicon. It's a type of very highly doped silicon. It's very highly conductive compared to normal silicon, right? But it's also what they make solar panels out of, okay? Now, they didn't used to always use polysilicon. They used to use metal for that. That's why they call it metal oxide semiconductor, MOS, M-O-S, MOSFET. MOSFET stands for metal oxide semiconductor, but they don't use metal anymore. They use polysilicon here now instead of metal. So they still call it a MOSFET though, which is not misnomer, right? It should be POS, right? But they still call it MOSFET. And okay, so anyway, what's the purpose of all this? Okay, well here's the thing where this is the part that's crazy. So if you put a positive voltage on the gate, the gate and the substrate are a capacitor. I mentioned there's also a capacitor between the diffusion and the substrate too, but there's also another capacitor between the gate and substrate because there's two conductors separated by a non-conductor, an insulator. So you might say, why are we doing this? Why do we need a capacitor? Well, you need the capacitor because capacitors accumulate charge. And when you accumulate charge in the gate, and this is the part I told you earlier, you got to accept this. This is the part that's a little weird. I told you that the majority charge carriers in p-type silicon are holes, right? But if you build up a charge in the gate, a positive charge, it will attract right under the gate minority carriers in the p-type, which are electrons. Somehow. There's minority carriers in there. So even though p-type silicon is mostly holes floating around, you can attract the little bit of minority carriers in there. And they'll collect. And you might say, why? Why? Well, because they're electrons. Electrons are negative. They're attracted to positive charge, right? So what ends up happening is I put a positive voltage on here, and electrons, the minority carriers, somehow that are inside p silicon, they'll collect in the channel. And because the minority carriers are holes, and because the majority carriers in the n-type silicon are holes, you'll form a conductive channel between these two diffusion areas, right? And that will turn the transistor on. It'll make it conduct from these two sides, source and drain, to get connected, essentially, right? Make sense? Now here's the problem though. There's a couple issues with this. Now first of all, as I mentioned, you have to build up charge to make that happen. Well, as you guys know, that takes time. Capacitors are slow. You have to accumulate charge. That's not good for the latest Apple chip that wants to be fast, right? So that's one issue. The other issue is I told you guys also that charge carriers do not travel at the speed of light. They're pretty slow, right? And so even once you put those minority carriers in the channel, you still have to make them move charge from one side to the other. And so the mobility is fixed. That's a physical property of the semiconductor. So the problem is, in addition to having to charge this bad boy up, the speed at which you can get things across depend on the mobility, how fast you can move. You can't change the mobility, but you can change how far they have to go. So if you make the channel, if you shrink that channel, then the charge carriers, which have a fixed mobility, you can't speed them up. I don't think there's any way you can speed up the charge carriers in a semiconductor, but you can give them a shorter distance to go. And so the shorter that distance is, the faster that thing will turn on, right? So you got to charge it, and then you got to get the guys going across the channel, right? So you want to make this channel as small as possible. And that's what that technology node is. When Intel says, we have a 7 nanometer process, that's what they're referring to, is the channel length, 7 nanometers. But that's not actually what it is, because as I mentioned, they're cheating a little bit. They're making a 3-dimensional channel, I think. They're doing this thing where the modern processes have this channel is they make it 3-dimensional. It's called a FinFET. So they've slightly altered the structure here to add another dimension here, right? And then they advertise it as having effectively a 7 nanometer channel, right? What's the actual channel size? What's the actual distance at an Intel chip? I don't know. It's probably still 90 nanometers, 45, something like that in reality. You guys with me? Okay, so that's the whole idea The only question is where does minority charge carriers come from? They're just in there. And you can attract them. And when you attract them, that's what turns on the transistor. Okay, so then you can have a PMOS. Oh, by the way, that's called an NMOS transistor because positive charge, right? But you can also build a transistor where the channel gets negative charge. And if you put a negative charge here, then you can attract the minority carriers out of an N silicon, right? If you make this negative instead of positive, and assuming this P is actually N, so what does that mean, negative? Well, that basically means that instead of a 1 to turn it on, a 0 turns it on, essentially. But it's not really a 0, it's actually a negative voltage. But we think of it as a 0 because it's 0 is negative compared to the reference, right? If the reference is VDD and I put a 0 as the input, I'm actually putting negative VDD in here, which is putting a negative charge here, which will attract the minority carriers. So that's called a PMOS. That's what this is. This is PMOS where you reverse these, right? So basically NMOS is an NMOS because the diffusion area is N. A PMOS is a PMOS is a PMOS is a PMOS because its diffusion area is P. And of course the bulk, which is the substrate, is of course the opposite, right? You guys with me? Now you might say, wait, hold on. What about the diode effect though? I mean, what happens, how do you prevent the diffusion areas from dumping all their current into the substrate? Or vice versa, the substrate dumping current into the diffusion areas. How do you guarantee that these are not electrically connected? Well, you have to bring the N, in this case, this has to go to VDD. So the substrate on a PMOS, you have to energize the substrate to VDD. That way, you got to have the voltage of the substrate higher than the diffusion areas to reverse bias those diffusion area diodes, right? Okay, now you might say, wait a minute, hold on. I thought you said the substrate is always P-type, though. You use P-type for the substrate. Yes, so the way you get around that is the substrate is P. Again, I don't know why they chose P. It's always been P. But if you want to make a PMOS transistor, which is the transistor that is the opposite guy, turns on when you put 0 into it, you create an N well, which is basically another diffusion area, except it's a deeper and bigger diffusion area of N-type material, right? So you create a localized substrate of N material, and then your diffusion areas are P inside of that. Make sense? So that's how you make it. And then, of course, N has to be set to VDD, and the P has to be set to ground, right? To make sure all these diodes are biased. And you might say, well, how do you do that? Well, to energize the regular to ground the regular substrate, you have to put a contact in there. So the P substrate has a contact to ground that goes through a P plus diffusion area. Right? What's P plus? It's more doped P. More heavily doped P. More holes. There's more majority carrier holes than there are here, right? And you might say, well, then what's the point of that? Well, it creates a nice contact. You have a wire that's metal, copper, aluminum wire, and you want to connect that wire to silicon that's more conductive. So I'm going to dope it really hard with P. And then I will embed it in a more lightly doped. So this creates a nice path into the substrate, right? And then I can make sure this substrate's grounded, right? Then, over here, when I have a well, the well is N. I put some N plus on there to make a nice little transition. And then I connect the N plus, I connect this to my wire. Wire goes to VDD. So that'll let me take this N well and take it to VDD, right? Make sense? So now, when you design a chip as a masks, shapes, polygons, right? You design it from the top down. You don't design it from the sandwich cutaway like this, or you do it from the top down. But you will have a layer for N plus, the diffusion area. You have a layer for N well. Then on top of the N well, you can put another polygon that's the P plus layer, and then you could put a layer for silicon dioxide, and then you could put a layer for polysilicon. So these are all built up from drawing polygons, rectangles mostly. We call them polygons, but they're really just the rectangles on top of rectangles on top of rectangles. Every one of those rectangles represents a layer, starting from the bottommost layer, which is the well, and then there's metal layers on top of this that form the wires, right? And then there's contact layers, which every layer is separated, well, not every layer, these ones aren't, the active layers aren't, but most of the layers are separated by by silicon dioxide glass, right? But if you want to connect two layers vertically, then you put a via, which is like a little hole, and that allows you to flow metal down, right? Or in this case, you actually have metal that flows down onto that contact there, onto that diffusion. So that's a layer. So you have a layer that's called a contact layer, which is this. Then you have a layer that's like metal 1, metal 2 contact, metal 2, metal 3 contact, metal 3, metal 4 contact. So basically, those are all your layers that you use when you design a chip. You just put those layers down. Make sense? Okay, so here's a question from a quiz. What type of silicon forms the body of a p-type transistor? Well, the answer to this is, remember, p-type transistor has p-type diffusion areas, so the body must be the opposite of that, so I'm guessing N? Yeah, right. MOSFETs are defined as N or p-type according to their, as I just said, diffusion areas. Okay, so, all right, so basically here's, this is what I just got done explaining. So I put VDD on the gate, puts a positive charge. Now this is a little confusing because I have plus signs here, but that plus sign is meant to represent a charge. These plus signs are meant to represent charge carriers. It's different. These pluses are not the same as those pluses, right? But anyway, I put a positive charge, and then that attracts the minority carriers, which are the holes in the channel, and the current flows, right? It's the same thing, by the way, that happens if you have two wires. If you hold up two wires and you put a big voltage differential between them, and you start moving them closer and closer, they won't conduct until eventually there'll be an arc, like of electricity. What that arc is it ionizes the air between the two wires, and those ions become the charge carriers, right? So it's the same principle as in semiconductors, right? You have the same issue in air that you do in semiconductors. You have to have charge carriers, right? Okay, so anyway, so we have two transistors then. We have NMOS and PMOS, and these are the symbols. And you can tell them apart because the PMOS has a bubble there. Bubble means active low or complement, whatever. Not, right? Okay, and then you have gate, source, and drain. Now, do we care about which is the source and which is the drain? Not really. I don't know why. Notice the drain is on the top for NMOS, and drain is on the bottom for PMOS. I don't know why. That's just a convention. You'll notice if you look at the cutaway view, the structure is symmetric structure. The transistor is symmetric. So if you call one the source and one the drain, it's up to you. That's a conventional thing, right? Okay. So if the gate is on, the transistor is on. If the gate is off, the transistor is off for NMOS, and then it's the reverse for PMOS, okay? Okay, so then how do you build a logic gate from this? Well, this is where things get really interesting. So basically, the inputs to the logic gate are connected to the gates of the transistors, right? Gate, logic gate, gate of the transistor. That's confusing. But the inputs to the gate are connected to the gate input, right? The inputs to the gate are connected to the gate input on the transistors. And then the output is connected to some source and drain of the transistors, right? So think of the source and drain as kind of the input, the outputs, and the gates are the inputs, sort of, right? But the way you set up a logic gate is you have to create two paths. You have to create two circuits. One is a pull-up network and one's a pull-down network. So you have to have a circuit that's responsible for shorting the output to VDD if the output of the gate is 1. And you have to have another circuit that shorts the output to ground if the output should be 0, right? But you can't do both at the same time. These have to be mutually exclusive, right? So only one of these networks can create a path between the output and one of the power, VDD or ground. Only one of them. If the pull-up and the pull-down network both provide a path, it's boom, blows up, right? You can only have one or the other, but ideally, always one of these will always be on, right? Unless you have a tri-state gate, which is a little kind of a specialized gate that you can get a floating output. But most gates don't have floating outputs. They have a 0 or 1 output all the time, right? You guys with me? Okay, so now the other thing you have to understand is that the pull-up network, and by the way, when you say network, it's circuit. Don't get confused by it. It's just a circuit. It's a circuit that creates a possible path through from the power supply to output or from the ground to output. But here's the other part you just have to kind of accept. Only PMOS transistors are good at pulling up, and only NMOS transistors are good at pulling down. When I say good, that doesn't mean you can't use NMOSs to pull up, but no one ever does that because they're awful at that job. They're too slow. The whole goal is to make these gates as fast as possible, right? So to make them fast, the PMOSs pull up and the NMOSs pull down, right? So what you end up having to do is create a circuit of NMOS transistors here and a circuit of PMOS transistors there, right? Okay. And you have to make sure that one thing I want to mention here, the same inputs connect to both, right? So you notice this fan out here. The fan out means I'm going to connect the inputs to both sides, right? Also, this is the thing that used to confuse me. These inputs are unaltered inputs. You have to take whatever the inputs are and use them in the gates on these networks. You can't add, extra inverters or anything like that. You have to take the raw inputs and connect them directly to these gates, right, on those transistors, right? Okay, so why is that relevant? Okay, well, let's look at an example of an inverter, just simple example first. So an inverter has a single PMOS pull up and a single NMOS pull down, right? So if the input, notice the input is fanned out to both, right? And then the output is connected to the middle node, right? So if the input is 1, it turns this guy on and this guy off, and thus the Y will be shorted to ground, right? That means it's called it'll pull Y down to ground. It's not mechanical. When they say pull down, it means that it's going to create a low resistance path to ground, right? And this R on, resistance of on, is like low, like a half an ohm, right? But the resistance of a transistor that's off is like 10 mega ohms, right? So what you're really doing here is creating a voltage divider, technically. But the way they describe it is, most people think of this as switches that are on or off, right? But in reality, it's a voltage divider. But I turn this guy on, that guy off, or that guy on, or that guy off, right? Depending on whether the input is 0 or 1. And thus, the output will be the opposite, right? So that's an inverter. Now, here's the problem. You would think you could build any gate with this, but you can't. The problem is that because PMOSs are responsible for pulling up, right? What that means, and PMOSs turn on when their input is 0. Okay? So what that means is if you look at the truth table here for a gate, and you look at all the rows that have a 1 output, okay? So this is a NAND gate. So I have 3 rows that are 1 and 1 row that are 0. This is the part that I used to hate about this stuff. In all 3 rows that pull the output up, at least one of the inputs has to be a 0. Because that's the only way you could pull up The only way you can short the output to VDD with a PMOS is to have a 0, right? So for every output row where the output is 1, at least one of the inputs has to be 1. Make sense? Likewise, for all the outputs that are 0, you got to have at least one input that's a 1 for the NMOS to pull down, right? Now what this means is that you're going to have a problem if you try to make an AND gate. Because an AND gate, its output is 0 when the inputs are 0, 0. Right? If I have an AND gate and my input is 0, 0, my output's supposed to be 0 because 0 and 0 is 0, right? That's not going to work here. Because if my inputs are 0, 0, none of these transistors can pull the output down. Right? Likewise, an OR gate. An OR gate will be OR gate has the output has to be 1 if the inputs are both 1, right? Because 1 or 1 is a 1, right? But that's not going to work because there are not going to be any PMOSs to set the output to 1 if you don't have any zeros in the input, right? So you can't make an AND gate and you can't make an OR gate, which is why we see NAND gate here, right? NAND gate you can make. NAND gate is just the opposite of an AND gate, right? So the way you do that is you put the two PMOSs in parallel, right? What that means is if they're in parallel, if either one of them is on, you're going to pull up. What does that mean? Well, remember, they turn on with 0. So if either input is a 0, pull it up. But then these guys are in series, which means the only way to pull it down is if both of these transistors are on, which is a 1, 1. So a 1, 1 will turn these guys on, pull it down, turn both of those two of those parallel guys both off, right? Any other combination of inputs will pull up because you're either going to have one or both of these guys turned off and they're in series. Does that make sense? So you'll notice that the pull-up network and the pull-down network are kind of opposite, right? One's in series and one's in parallel, right? It's basically the way that works. But you can't make, like I said, there's no way to make this is a negative logic gate. All CMOS gates are negative logic, right? Okay. So then you can make a 3-input NOR gate. That was a NAND gate I showed you before. This is a NOR gate and also has 3 inputs. So notice there's three NMOSs. NMOSs in series, parallel. These are parallel, and 3 PMOSs in series, right? That's a 3-input NOR gate. Now you can create an AND gate if you make a NAND with an inverter, but that requires 2 gates. You can't make an AND gate with just one pull-up, pull-down network. Make sense? What type of transistors comprise the pull-up network of a CMOS gate? Pull-up, P. Makes sense, right? P positive, pull-up, right? That makes sense. Which of the following Boolean functions can be realized with a single CMOS gate? I don't know. I have to build the truth tables to figure this out. So there's 4 options here. This is the 4 truth tables for those 4 options. What you want to look for is that anytime you have a 1, you got to have at least 1 0. So that check, that one's good. And if you have a 0, you got to have at least 1 1, right, in the inputs? Good, check, fine. That one's fine. How about this one? This one, 0, I have at least 1 1 in there, good. But the 1s, that one's a problem. That row right there disqualifies that guy from being a CMOS gate. Because you cannot have 2 zeros and pull the output out because the PMOSs won't. I'm sorry, no, that's right. No, that's right. I'm sorry, I had that wrong. I had that switch. This one, rather. 1 1, 1 1 0. That disqualifies it because if you have 1 1 input, there's no 0 in there to pull it up with the PMOS, right? So this is the one that disqualifies that one, right? Let's see. This one, disqualified. 0, 0, give a 0 output? No, you need at least one input to get a 0 output, because NAND is a pull-down network. And then, not NAND, sorry, NMOS, sorry. And in this case, pull up with a 0, yes. Pull down with a 1, yes. Pull up with a 0, yes. Pull up with no zeros. Oh, no, that one's disqualified, right? So only that first guy. And by the way, if you say not A and not B, if you remember De Morgan's law from 211, De Morgan's law says that's actually a NOR gate, that first option. So I kind of tricked you with that. That's actually just NOR at the top. Okay. Okay, so I'm out of time, right? Yes.